Welcome back to the energy conversion lectures. Inductance is an important term that defines and represents a magnetic circuit. Basically, any magnetic circuit such as a transformer or rotating electrical machine can be represented or modeled by some inductances. To elaborate on this statement, let's assume we have a magnetic circuit that consists of a coil and a magnetic material core. This magnetic circuit is supplied by an electrical voltage source through a resistance R as shown. Based on Faraday's and Lenz's laws, the voltage equation can be represented as follows. Now let's apply the following rules and formulas that we learned before to derive a new formula for the magnetic field linkage psi. As you can see, after some simplification and substitution, the following formula of the magnetic field linkage psi can be achieved. The term n squared over reluctance will be called an inductance or a self-inductance and is denoted by the capital letter L. From the new derived formula, the inductance L can be defined as a magnetic field linkage psi per unit current I. That means if the inductance is high, a high magnetic field linkage will be produced with a small amount of current. Just to remind you here that the magnetic field linkage psi is defined as the number of magnetic field lines phi that links to the coil's winding N. Now let's substitute this new formula of psi into the voltage equation V as follows. If we assume that the physical dimension N, L, and A and the material property mu of the magnetic material are constants, these variables can be taken out of the derivative and the voltage equation can be written as follows. Based on this voltage equation, it is very clear that the inductance represents the interface between the electrical circuit and the magnetic circuit. In other words, the magnetic circuit is simply modeled as an inductance and is used in the electrical circuit. From the inductance equation n squared over the reluctance R, we can conclude the following. The inductance L is related to the physical dimensions of the magnetic circuit such as the cross-sectional area A of the core, the mean magnetic path L, the number of winding N, and the property of the magnetic medium or the permeability of the medium mu. If we ignore the saturation of the magnetic circuit, the inductance value can be only changed if the magnetic circuit physical dimensions or magnetic property are changed. Inductance is not dependent on the electrical current and voltage applied to the magnetic circuit. Also, it is obvious that the inductance is inversely proportional to the reluctance of the magnetic circuit and directly proportional to the coil winding squared. Furthermore, the relationship psi equal to Li can be represented by the following curve. It is very clear that the inductance represents the slope of the curve. As you can see, the inductance can also be saturated because it is related to the permeability mu. Basically, if the magnetic circuit is saturated, the slope becomes small, or in other words, we lose the inductance. Usually, the inductance is assumed to be linear or constant to simplify the calculation of the magnetic circuit. However, saturation of the inductance considered one of the uncertainty and must be considered and compensated in some applications. If the saturation is ignored, a magnetic circuit can be called a linear magnetic circuit or a linear magnetic system. You may have noticed from the above magnetic circuit and the derivation of the inductance that the leakage magnetic fields have been neglected as part of some approximation. However, leakage magnetic fields can play big impact on magnetic circuit applications such as transformers and rotating electrical machines. Therefore, let's try to derive the electrical voltage equation and the inductance for the same magnetic circuit, but this time with the consideration of the leakage magnetic field phi L. The total magnetic fields that link the coil can be represented by phi and is equal to two components: the magnetizing magnetic fields phi m and the leakage magnetic fields phi L. Magnetizing magnetic fields represent the magnetic field lines that flow through the magnetic core, while the leakage magnetic fields represent the magnetic field lines that leaks through the air. The equivalent magnetic circuit of this magnetic circuit can be drawn as shown. RC represents the reluctance of the core, while RL represents the reluctance that opposes the leakage magnetic field. By applying Ohm's law to this equivalent magnetic circuit, the magnetizing and the leakage magnetic fields can be calculated as follows. Therefore, the magnetic field lines phi, the magnetic field linkage psi, and the inductance L can be calculated as follows. Where L represents the self-inductance, Lm represents the magnetizing inductance, and Ll represents the leakage inductance of the magnetic circuit. One rule you can learn from this derivation is that each magnetic field lines that is produced by the current I through the coil will be represented by an inductance in the electrical circuit. As you can see, the current I in this example produced two magnetic field lines, the magnetizing magnetic fields and the leakage magnetic fields. Therefore, these two magnetic fields have been represented by two inductances, the magnetizing inductance and the leakage inductance. Now, using Faraday's and Lenz's laws, the voltage equation and the electrical circuit can be represented as follows. Based on this equation, the inductance can be defined as the tendency of a coil to oppose any change in current. Another definition of inductance is the ability of a coil to produce electromotive force E by a variation of a current. Before ending this lecture, I would like to show you some examples about how the leakage magnetic fields and the magnetizing magnetic fields are flowing in some rotating electrical machines. At this point, you do not need to know more details about the electrical machine. However, all you need to know is that the magnetic fields that do not cross the air gap are representing the leakage magnetic fields, while the magnetic field lines that are crossing the air gap represent the magnetizing magnetic field or the main field that is used in generating the torque. As I explained earlier, these two magnetic fields will be modeled as magnetizing and leakage inductances in the equivalent electrical circuit of the rotating electrical machines. Last point you should know, and you will experience in your practical engineering life, is that these inductances play a big role in deciding the machine performance. Let's conclude this lecture at this point, and I will extend the inductance topic to include the multiple coils magnetic circuit in the next lecture. Thanks for your attention, and let me know if you have questions. I am Ihsan An-Nabi, and it was a pleasure sharing this lecture with you. Thank you.